Good evening. It is Thursday, April 3rd, 2025, and welcome to the 2025 Kamloops Exploration Group Lecture Series. My name is Sean Toom, and over the last couple months, KEG has been extremely excited to host some presentations from some fantastic experts. Before we get started, I would first like to acknowledge that we are speaking today from Kamloops within the territory of the Tk'emlúps-Teshishwapnik peoples, on whose land I have the privilege to work and play. This year's series has been hosted through a hybrid style with some of the online in-person events and as well as through Zoom, which we're obviously doing today. The next lecture series will also be over Zoom as well. As a nonprofit organization, the Kamloops Exploration Group relies on sponsors to aid in hosting such events. And tonight we would like to thank very much ALS Geochemistry for being one of the sponsors for the 2025 lecture series. I'd like to inform everyone that your microphones are muted and your video cameras are turned off. If you have any questions throughout the talk, please type them into the Q&A, and we'll get to that after the portion of the talk at the end. Tonight, we are extremely excited to welcome Connor Morison. If you would like to know more about Connor, his biography can be found on the KEG website. Connor graduated with a BSc from the University of St. Andrews in Scotland back in 2019 and followed that up with a MSc in 2021. Connor is currently working through his PhD at the School of Geosciences in Edinburgh and is working on understanding the environmental and societal impacts of the Elgia flood lava eruptions. He also has a strong standing interest in the hazard potential of the Mount Garibaldi, a long-dormant volcano in the Pacific Northwest. Connor's talk today, fittingly, is the Mount Garibaldi, a long-dormant volcano in the Pacific Northwest. Also to mention, Catherine Hickson's on the call. We'll speak with her later. Catherine is a Canadian volcanologist, formerly with the GSC, and again, we'll speak with her later in the question period. And with that, Connor, the stage is yours.
Well, thank you very much for that introduction. And I'll just share my screen. And just to clarify that you can see the screen?
Yes, it's good.
Excellent. And so I'm just going to move myself to the corner. Just to clarify that that you can't see me in the corner of your screen.
Nope. No,
No,
we just
okay,
see
that's
the
good.
full. Yep.
Excellent. Okay, so tonight I'm going to talk about Mount Garibaldi, as I said, and this topic has been a subject of increased interest over the last couple of years, and I would say some of that interest has originated from the publication that myself and Kathy produced 2 years ago. There was a review paper on the hazard potential from Garibaldi. And perhaps this captured the attention of the public in a way that was different from before because the framing is different. So when Western Europeans colonized North America 250 plus years ago, they entered into a landscape that was apparently geologically stable. And these paintings show this idea that this is a landscape that is not a threat, doesn't represent a threat. These are serene, prominent mountains with snow on them. In fact, in Steve Olson's work, book about Mount St. Helens, he described them as hooded sentinels above a green-clad landscape. This idea that these are not mountains that could potentially erupt. And yet we know that Mount St. Helens in the top right doesn't look like that anymore at all, after the 1980 eruption blasted the northern flank clean off. One of the other differences between then and now is the society has changed. in a way that is wholly unprecedented for future hazards. And that is something that we're about to discuss. So going back to Mount St. Helens, back in 1978, so the picture in the top left, you can see what Mount St. Helens looked like then. And there was a paper, a professional paper published by the USGS by Rocky Crandall and Donald Molyneux that suggested that an eruption at Mount St. Helens was likely before the end of the century. And this was based on, I think, primarily stratigraphic work based on the frequency of eruptions in the past. But this quotation here that was in a press, in the newspaper of the time, I was slightly poking fun at this idea that scientists don't know whether that eruption would be in a week's time or in 500 years. And this points to generally the idea of science. Science, we're not soothsayers. Volcanologists are not soothsayers. We base our interpretations on data, and that data comes from stratigraphic logs, from the geology, from deformation, geochemistry, gas emissions, and all the rest of it. So let's just have a look at the wider picture. This on the left is the Cascadia volcanic arc, and this is a arc of volcanoes located about 300 kilometers inboard of the Cascadia subduction zone, which is the location where the Juan de Fuca oceanic plate is being subducted incrementally underneath the continental North American plate. And these volcanoes are associated with that convergent plate boundary. And stretching from the north of California up to the south of British Columbia, there are some recognizable names. For instance, Mount St. Helens in the middle there in Washington, and Shasta in the south, Garibaldi being the most southern volcanic system in British Columbia. Now, what is this? The volumetric eruption flux. That is the amount of material, the amount of magma that can be expected to erupt from a volcano in a given period of time, in this case, 1,000 years. And I must stress, these are ballpark figures. These are significantly prone to error, particularly given the period of time they're referring to. But we can broadly say that Mount Baker, for example, has produced about 0.1 to 0.2 cubic kilometers every 1,000 years over the last 500,000 years. But more productive volcanic systems, such as Mount Rainier, Mount Shasta, are producing a little bit more. The most productive is Mount St. Helens by a long way, being 2 cubic kilometers every 1,000 years over the last 23,000 years. Now, put Garibaldi into that mix, and Garibaldi is producing about 0.2 cubic kilometers per 1,000 years, but that is only based on the last 13,000 years. Now, on that metric alone, Garibaldi is about as productive as the least productive members of the Cascades that I've got up here. However, based on all of this, science has been able to say with a reasonable accuracy that we can expect 1 or 2 eruptions in a century. Over the next 50 years, another Cascades eruption is expected, and science needs to investigate the possibility that it could be any one of these volcanoes that erupts next, and to anticipate the hazards that might be associated with that. And so I've said in the press that dormant periods between eruptions in Canada can be several thousand years long. And that is enough time, as I've said, for whole civilizations, such as the civilization that was established when Western Europe colonized North America. That is enough time for that civilization to come, arrive, and establish without ever realizing that mountains can erupt in this environment. Okay, so here's Mount Garibaldi on the right, and what we've got on the left here is by no means a prescriptive flowchart for the progression of science, but it acts as a guideline. And so when realizing that a volcano is potentially active, often it's a case of making geological maps, surveying the geology, and identifying the stratigraphy. So that's the geological evidence for eruptions. Now, Garibaldi went through this phase of science probably in the 1950s and the 1960s. This is followed up by petrological work, geochemical work, and work to establish what the physical volcanology is of a volcano. And I would say that we went through this in the 70s, 80s, and 90s. There is some still going on today, of course, but the bulk of this work was done before the 90s. And apart from very limited work that is talking about all of the above, no work yet, and I include my own paper in this, no work here has been able to produce a comprehensive hazard assessment for Garibaldi to date. But that is the next step. That is the next step at this volcano. And when hazards are identified, or if they're identified, they can then be monitored and mitigated. But it's also important in any consideration of vulnerability or hazards, that vulnerability in society is considered as well. And 2018, I undertook a very limited hazard perception survey in Squamish, very limited, and not published. But it allowed me to identify that there was very poor hazard perception for volcanic hazards in Squamish. And that partly was an inspiration for my own work. Once this has been done, this idea of acceptable risk, it's in a spiky box because it is a spiky subject. And it's not one that I'm going to dwell on at all. But there is an element of acceptable risk in any volcanic environment in the world. And that's the risk that a population is prepared to accept in return for being able to enjoy the benefits of where they live. And there is a trade-off and decisions that have to be made regarding living in a place. But once the full picture of what the hazards are emerges, and only then can hazards be mitigated as well as vulnerability to produce this holy grail of preparedness. So let's establish what the geological framework is of Garibaldi then. So on this map on the left, we've got 3 volcanic systems. We've got Garibaldi in the south, we've got Mount Cayley, and then Mount Meager further north. And they are roughly arranged south-southeast to north-northwest across the sea to sky region from Vancouver to the north. And the different colored spots there are vent locations that we know about in relatively recent history. And on the right, again, that's a zoomed in version showing the area immediately around Squamish, which is highlighted in the zebra stripes. And the recent geology I'm going to refer to in the black here is the Ring Creek lava flow. And then these two lava flows here around Garibaldi Lake, the Barrier lava flow and Culleton Creek lava flow. And this is what this area looks like in 3 dimensions. This is looking from the Barrier, which is this escarpment here, looking broadly south towards the American border. And this is the high terrain of the Mount Garibaldi system. We believe that about 13,000 years ago, an eruption started on the western side, the western shoulder of Mount Price here, Clinker Peak, and one andesitic lava flow started heading north into this valley here, that's Rubble Creek, into this valley, and starts to spread out, dams the valley, hence the reason why Garibaldi Lake forms in the background. But you can see this escarpment here, this, which is known as the Barrier, is most likely a result of impoundment against ice located in the valley, in the main Cheakamus Valley. And that gives us the approximate age of the lava flow, of being at a time when ice was retreating from the valley, but had retreated most likely from these alpine areas. And then to the south, another lava flow of a similar composition headed south into the Warren Glacier area. We know that the Warren Glacier was not present in this valley, as it isn't today, because there's no evidence for ice contact with this lava. And the lava headed down this valley where it was dammed up against the ice in the valley. So let's take the Barrier lava flow. So that's the northern lava flow. This is, here's some photographs illustrating this. There is the vent area, and you can see here the lava flow has channeled itself by levees before spreading out, and you can see these arcuate ridges indicating the flow direction downwards into what was a valley and is now Garibaldi Lake. You can see those ridges there heading downwards into the subsurface of the lake. And this image here was taken on a very smoky day, I remember, back in 2018, of the surface of the lava flow, comprising these huge blocks of andesitic lava. And in B, this is the 250-meter high escarpment known as the Barrier. Taking this lava flow in 3 dimensions, and I must stress these are estimates of the thickness of this lava flow. Lava flow started just above P here on our map and headed towards L. And if we take a cross section at P, which is near the start of the lava flow, that's this graph at the top left, we can see these levees that the lava has created where it's channeled itself, transferring molten rock downwards to the lava flow front. And you can see here it begins to thicken as it's impounded against the ice in the valley to a depth of 250 plus meters. And then begins to thin again as it turns round the side of the mountain where it's not impounded by the ice. And the very front of the lava flow looms above the forest of Conroy Creek, where it stopped. And the southerly lava flow from Clinker Peak, much less well studied, barely visible from the sea to sky highway is here. And this is a reconstruction showing that ice that we suspect was in the valley. Looking north to Black Tusk there, Whistler just beyond. And we remove the ice, and this escarpment is what remains. And these escarpments, it has to be said, are incrementally adjusting to these post-glacial conditions, and have been now for the best part of 12,000 years. And in 3 dimensions, we can see a very similar story. The levees that are channeling the lava downhill as it meets the glacial outwash of the Warren Glacier, and then heads down into this V-shaped valley where it thickens. And it thickens because it's being impounded by the ice to a depth of possibly up to 400 meters thick, which is really thick for a lava flow. And finally, the final lava flow I'm going to discuss tonight is the Ring Creek lava flow. And that emanated from Opal Cone, located on the southeastern flank of Garibaldi, headed south into this valley, and then westward into the main Mamquam River Valley. And you can see these jointed structures underneath this forest here. And the chemistry of this lava flow was a little bit different in that it was more silica rich. And some authors, though not all authors, have identified this as a dacite. Indeed, it is the longest dacite lava flow on Earth. And it's worth bearing that in mind for a little bit later on when we talk about the hazards. But this lava flow has been dated by radiocarbon dating of a charcoal fragment in the river. And we've recalibrated that date due to the changing concentrations of radiocarbon in the atmosphere to 10,300 to 12,700 years old. And a final look at the cross sections for this lava flow. Again, we've got the levees, very prominent levees here as it heads down into the valley. But you can see that it's not constrained by the topography. Okay, it would become constrained by the main valley, but you can see that it's not really touching the edges of the valley. It's constrained by within its own course. And the key difference with this lava flow is that it was not impounded by ice in the valley, which helps to date it further. We know that it is certainly after the period that we've just looked at. Let's add the lava flows then to the provisional hazard assessment. Based on the geochemistry, on what we know about how dacites and andesites flow elsewhere in the world, we can say that these lava flows in all likelihood would have taken years to form. But there are some odd anomalies, such as the length. Dacites don't typically travel more than immediately around a vent. So to be able to travel so far is certainly worth future research. And particularly with these ice impounded lava flows farther north, would they flow differently today if they weren't being impounded by ice? Moving on then to meltwater, and I'm not going to say much about meltwater because it's almost like a secondary volcanic hazard, but it's suffice to say that meltwater is almost certainly a hazard whenever glaciers or snow continues to clad these potential vent areas around the volcano. And inevitably, the areas that are most exposed to floods are the areas that are in or near existing waterways. And those are the Mamquam, Cheakamus, and Chekai rivers, all of which discharge through Squamish. So Squamish is potentially the most vulnerable place to be for meltwater flood risk in the event of an eruption. But future modelling will be able to pin that down a bit more. So let's add that to the hazard assessment. Now, pyroclastic density currents, or otherwise known as pyroclastic flows, are superheated clouds of gas, ash, and rock that explode violently from a volcano and travel downwards through the topography, and are extremely destructive and dangerous to life. And the fact that Garibaldi does produce pyroclastic density currents is not a new idea. This was an idea that very much was illustrated by Bill Matthews in 1952. You see Black Tusk is up there in the top left. Here's the Sea to Sky corridor. Squamish would be down here. And here's pyroclastic flow coming down the side. And these, in all likelihood, were generated by the collapse of these dacite domes which form on the summit, resulting in explosive decompression of the magma lying below. And there is evidence for these pyroclastic density currents still remaining at the margins of the present day residential area of Squamish. And these take the form of jointed dacitic blocks in this deposit with quenched margins. And that infers very quick, hot emplacement of volcanic material, which is high in silica, most certainly from Garibaldi. And the fact that these deposits have these little holes, these vesicles in them, indicates that it was hot. There was steam and it was escaping. So this is not a glacial feature. This is not a river feature, and it's not remobilized material from somewhere else. This is a primary volcanically emplaced material that has been dated in past work, again, radiocarbon date of a wood fragment, to this window of opportunity between 11,600 and 11,800 years ago. So let's add pyroclastic density currents to the hazard assessment. And the final hazard that I would like to discuss this evening is tephra fallout. And this is actually my main research area outside of the Garibaldi field. And what is tephra? Tephra is the explosively ejected volcanic material, fragmented rock from an explosive eruption, often, but not always, silicic, or at least in this region, it is most likely silicic tephra. And the presence of ice and snow in these vent areas is not going to assist in terms of hazard mitigation, because ice and snow makes tephra, or volcanic ash, it makes it more fine when it erupts through ice. And volcanic ash can have particularly egregious impacts on vegetation, as you can see here after the eruption of Mount St. Helens in 1980. Transportation, it can impound water courses, block water courses. It has various impacts on glaciers, as well as on human and animal health. For instance, tephra in the air and tephra in the water. This image is taken from 2 years ago in Russia after an eruption that produced tephra, most likely silicic. You can see here that this is landed on the roofs of these properties. The weight of tephra, which is about 2.5 times as heavy as the equivalent volume of water. And believe me, I know, because I had to carry about 10 boxes of the stuff across an Icelandic moor 2 years ago. So it's heavy. And this fallout can lead to roof collapse as well as crop burial, particularly during the summer months. And tephra does extremely bad things to power lines as well, because tephra is more conductive, resulting in potentially power outages in the region that it has affected. This photograph, which looks like a Airbus 320 in Indonesia after a explosive tephra producing eruption, grounded air traffic, shows the aircraft covered in ash. Ash is particularly egregious to working machinery, and particularly aviation. Pilots have to be able to see to fly. Air traffic control has to be able to see to direct aircraft. And if it can't do that, then there are dangers to aviation. Furthermore, ash intake into jet engines can result in the failure of the engines and a loss of thrust during flight. Passing through an ash cloud can result in irreparable damage to frosting to the windscreens of an aircraft, to the radar on the front, and to the leading edges of the wings. And the weight of fallout can actually tip aircraft over on their, where they're standing as well as result in reduced friction on the runways and the taxiways. So all in all, you don't want to be flying or trying to use mechanical equipment in these situations. This is a image, I believe, taken in Yakima after the 1980 eruption of Mount St. Helens. Middle of the day, I think. So you can see that it is a widespread hazard, the most widespread hazard from a volcanic eruption of this nature. Now, normally, to be able to identify whether volcanoes have been prone to this sort of activity in the past, we dig holes in the ground and we identify these beds of volcanic ash in the ground under the assumption that the longer ago is farther down in the ground. And in BC and Alberta, if you dig down, you're most likely going to find the Bridge River tephra initially at the top from an eruption of Mount Meager about 2,500 years ago. And this fallout headed eastwards across the Rockies. Potentially, depending on where you are, you're going to get a very large eruption of Mount St. Helens about 4,000 years ago. And then most locations in North America will have received some Mazama ash from the eruption of Mount Mazama that produced Crater Lake here down in Oregon 7,700 years ago. And these images from Britta Jensen's work a few years ago. But no Garibaldi tephra layers have been found in the region. And what does this imply? Does it imply that we just haven't found any? Does it imply that the eruptions were not explosive? Well, we know that they were because we have pyroclastic density currents and evidence for those in Squamish. So that leads me to suspect that the evidence has been destroyed in this region following the retreat of the last vestiges of the last ice sheets. And retreating ice is not conducive to tephra layer preservation, but it remains to be seen whether or not there are Garibaldi tephra layers out there somewhere. So let's add that to our final slot in the provisional hazard assessment. And so here we are. We've arrived at the almost at the end with lava flows, floods, pyroclastic density currents, and tephra fallout being all potential hazards in this volcanic area. And if we look at this on a timeline, starting from now at 0, if we go back a bit, we've got the 2010 Winter Olympics. Back a little bit more, we've got George Vancouver landing in BC in the 1790s. A bit more, we've got the most recent Cascadia megathrust earthquake in January 1700. A long way before that, Mount Meager erupted, and thousands of years before that, we get to the most recent known Garibaldi eruptions. Now, these red areas, as I explained earlier, that is not the period that Garibaldi was last active. Those are just windows of opportunity where we know Garibaldi erupted. And there is a subtle difference. The last eruptive period, we know, produced a dacitic lava flow from Opal Cone between 10,300 and 12,700 years ago. Possibly at exactly the same time, possibly before or possibly after, Garibaldi itself erupted, producing dacite domes at the summit and pyroclastic density currents down the western flanks. And this scenario is not new. This has been well known in the scientific literature since the 1950s. But we cannot yet rule out whether these events happened at the same time, whether they were just before the Holocene, and we can't date them any more precisely than that, or at least no one has been able to thus far. But this uncertainty, this great uncertainty on the last eruptive period, has a bearing on how comparable Mount Garibaldi is in comparison to other volcanoes in Canada and internationally. And this is something that that we're going to develop in a very imminent discussion publication that Kathy Hickson and I have just completed based on the nationwide volcano threat assessment published last year. And I'm not going to talk about that just now because it hasn't been published yet, but it is imminent. And if anyone is interested in reading about this uncertainty a bit more, then I would encourage you to download it. And so dawn is very almost breaking here in Scotland. It's just approaching 3:45 in the morning here. So I'm going to end there. And if anyone has any questions, please don't hesitate to ask us. Kathy and I will be on hand to answer them. Thank you very much.
Thank you very much, Connor. It was a great presentation. If anyone has any questions for Connor, please type them into the Q&A and we'll get to them shortly. One of the things that I think about, Connor, when you showed one of the first slides was the article from whoever it was talking about Mount St. Helens back in 79 when Helens exploded in 80, about how it's, it could be next week or 500 years. And so I wanted to ask you, what your thoughts are on understanding Garibaldi. Is there any sense of when that might happen?
No, yes, it is possible to give a probability, but that probability would be based on it would be based on very few eruptions right at the start of that period. We're talking about 10,000 years ago. That probability would be based on data points that would give a meaningless number. So it's very difficult. Kathy, would you add anything?
Yes, so Molyneux and Crandall have been working on Mount St. Helens for about 10 years, and their studies were on, volcanic stratigraphy. It was very clear from those studies that Mount St. Helens was a very youthful volcano, as well as one which erupted quite frequently. Remember, it's south of us, so it doesn't have the same kind of, it does have glaciers, but it doesn't have the same kind of glacier, and it didn't have a continental glacier that basically exhumed significant valleys on either side. So Mount St. Helens definitely had preserved its history of volcanic eruptions. Garibaldi were, prior to 10,000 years, those events have been essentially obliterated by glaciation. So we don't have a good feeling. What we do know is that since the last, the withdrawal of the Fraser glaciation, that there's been some very curious things, like that pyroclastic flow that Connor showed you the picture of. That's actually, we found that doing field work in one of the gullies very close to the golf course at the north end of town, and it's very clear it had never been identified before. It was hot. And it was post-glacial. It could have been simply a collapse. So if you, from that point, if you look up at the mountain, you'll see it's very, very thick, and it takes thousands of years to cool from an eruption the size of what occurred at Garibaldi. So it may simply have been a landslide of hot pyroclastic material from an eruption during the Ice Age, and but basically was no longer buttressed by the glacier. So there's some very intriguing things at Garibaldi, but to preface this, or to we don't see sulfur, we don't see thermal anomalies, we don't see hot springs, and all of those were present at Mount St. Helens. So some of the hallmarks of St. Helens to tell us that it was a very active volcano, we just don't see. But how many of those hallmarks are actually missing simply because of glaciation?
Thanks for answering that. I don't know how many people in the crowd here have flashbacks to 1997, Pierce Brosnan, Dante's Peak. I know I do. And I
Yeah,
wanted to ask about, the conditions that you're talking about, the sulfur, the hot springs, all those things that were also in Dante's Peak. How fast would those things potentially occur? Like, what would be the fastest timeline that you'd expect to see acidification of Garibaldi Lake, sulfur forming on the flanks of the volcano, name the thing. Like how fast could that form before an eruption?
Connor, you want to take a stab? Andy Lockhart was the volcanologist who was he was the consultant for Dante's Peak. All of us had a hoot when it came out. I used it as teaching material. So essentially, go off, watch Dante's Peak, come back and tell me what you think was real and what was possible.
I thought it was all real. I thought it was all real.
But Connor, you want to answer that?
I'm not sure. So,
Yeah, he's too young. He's too young.
yeah,
He
I might
doesn't have a
pass on that.
clue what we're talking about.
Well, it's all good. I mean, I guess the question would have been, that's just comic relief, but
Yeah.
like how fast can you expect these kind of phenomenons to occur in a volcanic system when you expect, those things, like the things I mentioned? What is the timeline that you'd be able to see that on? And do you think that people would be able to pick that up in advance at a place like Garibaldi, considering what their monitoring might be?
So assuming that monitoring did pick up earthquakes are a harbinger of eruptions, then you could expect earthquakes to start occurring years, possibly even decades before a volcanic system like this wakes up. I'm just thinking back to something also familiar with me is the Eyjafjall volcano in Iceland, which erupted in 2010, was showing elevated seismicity in 1994. So it was waking up for over decades before it actually erupted in 2010.
Yeah, and if we look at Mount St. Helens, similar. So, in fact, Steve Malone was one of the major seismologists, USGS, University of Seattle, and he actually went back through the records and saw that there was a seismic activity that, in hindsight, was definitely associated with the awakening of the volcano. So we will get some warning. The monitoring network, it's depending on how sensitive the monitoring network is, but certainly once the magma starts moving, we will definitely we will see some seismicity, and then how quickly things like fumaroles or hot springs, the acidification of Garibaldi. No, sorry, that's not on. But but and we're not driving jeeps through lava flows.
It was a Suburban, but semantics.
Oh, sorry.
Yeah.
um, but those things will happen when we're actually seeing a fair amount of seismicity, because they're related to fracturing of the upper edifice of the volcano and the release of gases and whatnot. And so those come fairly soon in terms of when we start seeing significant seismicity. So we will get warning.
Okay, thanks for that. I'm sure the people of Squamish would be happy to hear that as well. Are there any equivalent regions? Some questions coming in now. Are there any equivalent regions elsewhere in Canada where we have such concentration of volcanoes?
I think Kathy, you're the best one to answer this, because Kathy's done the most work, obviously, in this pairing in Canada. So, Kathy.
Yes, so it depends on how you. So the northern end of the Cascade volcanic arc, what we call the Garibaldi Belt, has large volcanoes, with Mount Silver Throne being a very large center at the northern end. If we're looking at the compositions of these volcanoes, we see actually rhyolites and dacites. But if we go north, the largest, most voluminous volcano in British Columbia, in Canada actually, is Level Mountain. And Level Mountain is a massive volcano. It's north of Mount Edziza, and it is north of Stewart, west of Dease Lake. Essentially, if anybody knows where that area is, there's a huge volcano up there, but it's actually andesitic and basaltic to andesitic in composition. So we in fact have our most recent volcanoes up in that neck of the woods. The Iskut River cones probably erupted a couple of hundred years ago. We got Siax, again 1700s is probably when that one erupted. So we have these volcanoes in the north, but mostly basaltic to basaltic andesite in composition.
Okay, thank you for that. And next question. I know that, well, I assume that Mount Garibaldi, I didn't catch it in the presentation, but I think it's a stratovolcano. And stratovolcanoes, what is the expected lifespan of these things? We talking tens of millions of years, millions of years? How often are they erupting, active, and then when do they die, or do they die?
So that's tricky because it's a contended topic. The topic is a moot point in volcanology when a volcano has gone extinct. But I would argue that if a volcano is still part of the same region, the same arc, and there are other volcanoes erupting within that arc, then it is potentially active. Most of Garibaldi that we see above Squamish probably relates to eruptions 20,000 years ago and a bit longer than that ago. Kathy, how old do you think Garibaldi is?
Well, we know,
Eruption.
yeah, probably a million. We know that Mount Meager, for example, is in the, the 2 to 3 million year old range. So, so these are very long-lived features, and I think you have to look at it from the perspective of, as long as there's subduction, there's a driving force, and we have volcanism. So, and it's really the rate of subduction which is driving the volume of material. So we're not in a very our subduction zone here is about 2.5 centimeters a year is what our subduction rate is. And so our volume of eruptions are significantly less than they are, say, in the Andes, which has, I think it's a 7 or 8 centimeter per year subduction rate. So,
or even, I was going to just jump in there, that when I talked about Mount St. Helens earlier on, Mount St. Helens being further south, the subduction there is probably faster. The rate that the downgoing plate is being subducted is probably faster, and that's resulting in the higher magma flux at Mount St. Helens, or it's certainly contributing to it. And of course, further north, the rate of subduction is arguably less, and so you have less throughput of material to erupt. Do you agree with that, Kathy?
Yeah, I mean, and remember that we've got a triple point off the northern end of Vancouver Island, so that we're moving from a a subduction to a transform margin. And before we were off this call, I just finished a report on the Northwest BC where this Iskut-Unuk River cones are, and it's sort of interesting because it's in a probably an extending rift zone. So different, that's why we're seeing different magmas, basaltic andesites. We're not seeing these evolved dacite, for example, in that area, and quite young. So the flux rate is related to subduction, but also, okay, look at Iceland. I mean, you're on a rift. And so are we looking at an incipient rift in northern BC? Possibly. That's certainly what the evidence suggests to us, is that we're actually looking at a pull apart zone in that neck of the woods.
Yeah, it's kind of consistent with, I'm an economic geologist, so I deal with these as a fossilized system, and we're using zircon ages to help us out with that, and you're plus or minus a couple million years, but we know that these systems are usually active hydrothermically for a couple million years at the most, kind of thing.
Yeah, and when we do work on magma chambers, that's what we see is these large magma chambers take about 1 million years to cool.
Yeah, yeah. Another question here. Someone was recently near Wells Gray, and they recently learned about the tuyas while in Wells Gray Park, and they want to know if there's any more evidence of tuyas near Mount Garibaldi. And do the tuyas tell you anything about anything else besides how thick the ice sheets it erupted through was?
Well, there's the table. The table is a tuya, and the table is located just on the, what would it be? It would be the eastern side of Warren Glacier, and just to the south of Garibaldi Lake.
And And there's
Yeah.
several more to the north as well. So this is actually one of the hallmarks of Canadian volcanism, is subglacial volcanism, not necessarily well-developed tuya forms. And I'm glad that you learned about the tuyas. That's where I did my PhD. And of course, the tuya, the name tuya, comes from Tuya Butte up in the Tuya-Teslin region, which is in northwestern BC. And that was identified by Bill Matthews. So he was one of the first people in the world to really see these flat-topped, steep-sided volcanoes and understand or recognize that they were related to eruptions through and into a glacier. An interesting story about that is during the war, so he was working up in northwestern BC. He saw the tuyas there. At the end of the war, he ended up in Iceland. He saw them there, and he had the aha moment, and that was how he put together the fact that, you know, these are subglacial volcanoes. So now it's interesting because internationally, in volcanology, these kinds of volcanoes are referred to as tuya, after Tuya Butte in northwestern BC. I don't
If
think the
anyone,
Icelands are very happy, but
yes, so good to say, I'm going to pick up for Iceland here because most of my research is in Iceland. Iceland has this tuya called Herðubreið. If anyone's been to Iceland, then they will remember it if they've been to that region. But I would definitely recommend a trip to Herðubreið if anyone is going to Iceland.
yeah, it's spectacular and definitely worth it. But we've got some fabulous ones up in the north. They're just a little bit more difficult to get to than Heidelberg.
Well, I got to fly to Iceland. There's that, you know. So next question, I guess it's always fun to hypothesize. What would be your categorization of risk between earthquakes in the Cascades versus volcanoes? Which one is more likely to affect folks that are living there?
Okay, so that depends on where you are, and it goes back to a lot of what I said earlier, in that it also depends on who you are and where you live and how you live. And earthquakes are a certainty in this region based on the location up and down the subduction zone, which is responsible for some of the greatest earthquakes on Earth. But the thing is that they happen so infrequently that people don't remember, or they maybe never experienced an earthquake. I realized that there was an earthquake a few months ago in British Columbia that may have served as a wake-up call that the region is seismically active. Volcanoes are much less likely to be a hazard in Canada, but the threat, assuming that a hazard happens, the threat of a volcano that a volcano produces is most likely more significant immediately around it.
Good answer.
Yeah, and I'd add to that we are on a subduction zone. You know, everybody talks about the big one here. That event that we had a few weeks ago was kind of a wake-up call, I think, to remind people. Certainly, when I worked for the GSC, earthquake hazards was a big thing that we were trying to get across to people, that we in the Lower Mainland here live in an earthquake hazard zone, and we did a lot of work back in the day to educate people. You know, a significant amount of public works were commenced because of the work of the GSC in terms of, you know, understanding, and then of course, you know, our last big one was the 1700 event. So, you know, are we overdue? Are we not? It's a little bit, but like, you know, is the volcano going to erupt tomorrow, or is it going to erupt in 500 years? We live in a subduction zone. As I tell people when they're traveling and they say, oh, you know, should they be worried about volcanoes? If you are traveling in an area of mountains, those mountains didn't just grow up out of the sea. They did so by a series of earthquakes. So if you're traveling in mountains, expect earthquakes and be prepared.
So drive a Suburban, right? I think with that, that's a good place to probably end it. Thank you so much, Connor, and thank you so much, Kathy. On behalf of the Campus Exploration Group, I'd like to thank everyone for joining us tonight. We'd like to thank again our sponsors, ALS, for sponsoring the whole 2025 KEG Lecture Series and supporting the series. It's very much thanks to them. Connor, thank you so much for joining and opening I guess, you know, we're the second to last speaker series now, but thank you again. We are grateful to have you here and share your knowledge and experience on Mount Garibaldi. Our next talk will be April 24th with our guest speaker, John Clegg, presenting landslides into lakes, rivers, valleys in BC, an unappreciated hazard. For more information about the KEG lecture series, please go to KEG, www.keg.bc.ca, and we appreciate comments and feedback, which can be submitted to kamloopsexploration@gmail.com. Thanks again, Connor. Thanks again, Kathy. Everyone have a good night.